27D, numbers 4 through 6. Many observational studies conclude that low-fat diets protect against cancer and cardiovascular events, which are heart attacks, strokes, and so forth. Experimental results, however, are generally negative. Meaning, do we reject the null? No. We say the difference is totally explainable by chance variation. In 2006, WHI published its results. This was a large-scale randomized trial on women who had reached menopause. As one part of the study, 48,835 women were randomized. 19,551 were assigned to the treatment group and put on a low-fat diet. The other 29,294 women were assigned to the control group and ate as they normally would. Subjects were followed for 8 years. Wow. Among other things, the investigators found that 1,357 women on the low-fat diet experienced at least one cardiovascular event compared to 2,888 in the control group. Can the difference between the two groups be explained by chance? All right. So, on the treatment side, we have 19541, and the percentage is 1357. What does that give me? What did you guys get when you did that? What percentage of the low-fat people had heart attacks? What is it? 6.9? Okay. Then on the other side, we have 2088 divided by 29294, which gives a percentage of 7.1. Okay. So, is there a difference between 6.9 and 7.1? That's going to be our null hypothesis. So the null says that the difference is equal to 0, and the alternative says the difference is greater than 0. Okay, so apparently these people did their homework. They randomized it. We're going to assume they did it correctly. They talked to lots of people, which is nice. And they ran this test for 8 years. Is this test blind? Probably not. Right? They're probably not going to their house and feeding them food and telling them whether or not it's low fat or not. Probably not going to happen. Okay? So that does create some problems, but we'll run the numbers and see what happens. So I need SDs. I'm going to do the square root of 0.069 times 0.931. Then on the other side, I want the square root of 0.071 times 0.929. What do you get when you do that? Did we not get this far? 0.254. And then on the other side, so those are really close to the same. Okay, so now I need to create SEs. So I divide this by the square root of 19541. And are these SEPs or SE averages? SEP, so when you do the division, you take your answer and turn it into a percentage. What do you get? 0.115. And on the other side, when you divide by 29294, you get 0.116. Okay. Now what do we do? I have the SEs from both samples. I need the SE for the difference. So I'm going to take the square root of 0.115 squared plus 0.116 squared. And again, the answer is going to be bigger than the average, but smaller than the sum. And it's about halfway. It's not really halfway. It depends on the numbers and everything. So you have to do this. You calculate it, and you end up with 0.164%, right? Okay. So we now do our z-test, our two-sample z-test. We expect 0, and we actually have 0.2. Okay, so I'm going to take 0.2 and divide it by 0.164. What is my z-score? 1.158. Okay, and then I shade norm from 1.158 to 5, and I get a p-value. You stop there. Somebody look in the back. Tell me what the p-value is. Um, 515. We're getting near the end. Okay, number 4. Oh, it doesn't say. It just says the difference is not significant. Okay, so we get a p-value of 12.3%, which is bigger than 5, which means we accept the null. Did a low-fat diet help? No. There was a difference, but it wasn't very big. Okay, so what's really going on? And this is kind of a conundrum in the dieting world these days. Turns out that fat was not the problem to begin with. It's the sugar that's the problem. Now, they thought it was fat because sugary things are often fatty things. And so they assumed, oh, hey, these people have unhealthy levels of fat in their blood and in their body, so it must have been fat that they were eating that caused it. But your body converts everything into sugar. Fat, protein, all carbohydrates get turned into glucose, and then your body uses glucose to as energy. So everything gets converted to glucose, including fat. But sugar gets turned into glucose so quickly that your sugar levels spike. And whenever your sugar levels spike, your body says, oh, this person is eating a lot of food, which is not really true. You're just eating a lot of sugar. So if you eat a huge dinner, then your body says, whoa, this person thinks there's going to be a famine next week, so we're going to store all this extra energy. So when you eat lots of sugar, your sugar level goes up and your body freaks out and says, hey, we need to pump out extra insulin because we have to capture all of this extra energy because next week there's not going to be any food, which is not true, right? So two things happen. First, your body produces so much insulin that the insulin stops working, which is called type 2 diabetes, as opposed to type 1 where your body just quits producing insulin. And the other thing is you store all of this extra stuff. So sugar gets turned into glucose, which gets turned into fat. Fat gets turned into glucose, which gets turned into fat. The only thing is it takes a really long time for fat to be converted into sugar. So you drink some whole milk and that fat all gets turned into sugar, but it takes a long time to do it. So you stay full and your body doesn't have this sugar rush. So the problem with low-fat foods is they taste terrible because fat holds flavor. So to make them taste better, what do? They put sugar in it. So you'll see a product that says 75% less fat, which means they had to put a lot of sugar in there, some of which might not even taste sweet. And you eat that, and your sugar shoots way up high, which means you create more fat after the fact. So anyway, turns out the low-fat diet doesn't really do it. Now, there's another really important thing right here. Do you remember months and months and months ago where I said sometimes you can talk to too many people? Okay, this is an example. So let's say that I change this to 7.15, okay, which is going to do what to this? If I widen the difference, it's going to make my z-score further to the right, and I don't know how far it's going to go. But let's say it goes to 1.7. 1.7 is going to give us a p-value of like 0.4 or 4.5, which tells us we need to reject the null. Okay? Now, how big is that difference between 6.9 and 7.15? It's tiny, right? It's like a fifth of a person. So even though we reject the null, do we really care? No. Okay, let me give you another example. Let's say we're testing two drugs. So drug A, or we're testing a drug, and then we have a placebo. And we want to be really sure it works. So I'm going to talk to 50,000 people on both sides. Okay? And I get a score for this, which is 28.2. And I get a score over here, which is 28.15. Okay? I calculate the SDs, and I take my SD, and I calculate it by the square, divide it by the square root of 50,000. This number is going to be very small. Would you agree? When you talk to 50,000 people, your SE is small. So I don't know what it would be. Like, let's say it's 0.006. And I do the same thing over here, and I get an SE of 0.005. Well, I'm going to make this easy on myself. I'm going to say 3 and 4, which makes the SE difference 5. So my SED is 0.005, Pythagorean theorem. Okay, well, let's do our normal curve. So we put a 0 here, I subtract those, and I get 0.05, right? Now I divide that by 0.005, and I get a z-score of 10. So my z-score is 10, which means my p-value, how much area is over here if this is 10 SE differences? 0. And I run out and I say, drug A works. There is a highly significant difference between the result with drug A and the placebo. And that's true. But what do you think? The actual difference is so small, nobody cares. Right? Why did that happen? It happened because my SEs are tiny. Why are my SEs tiny? Because I talk to so many people. So you would be much better off to get rid of a factor of 100 and talk to 500 people. Much easier, right? Much cheaper. Well, if I take these zeros off, what's going to happen? My SEs are going to be quite a bit bigger, so I end up with like 0.6. And over, oh, let's make it easy, 0.3. And over here, I get 0.4, which means this one is 0.5. Now, when I compare the difference of 0.05 with 0.5, so 0.05 divided by 0.5 is 0.1. Where is 0.1 on the normal table? It's like right here. How much area is from 0.1 to 5? almost 50%, right? So is there a difference between the drug score of 28.2 and 28.15? We accept the null because my p-value is really close to 50%, and we say, no, there's no difference. So talking to less than 100 people is problematic because you have to use a t-table and you have to create an SD+. But if you talk to more than 625 or 1,000 or 2,000, it just depends on what you're doing. But eventually, you can talk to so many people that you reject the null, when in reality, the difference is so insignificant, nobody cares, right? Are you going to run out and pay for drug A? No, probably not. If it's expensive, definitely not. Does it help? Statistically, yes, but the difference is so insignificant that nobody is going to care. So you have to be careful about talking to too many people. Because if you talk to too many people, you might get a result that, while statistically significant, doesn't actually mean anything in the real world. Right. It's statistically significant yet meaningless. So remember back in the early chapters when they talked to like 12 million people? That was a terrible idea. And it didn't work because they talked to the wrong group of people. But even talking to that many people doesn't really help you, which is why they don't anymore. Now they just talk to a couple thousand and they call it good. Okay? All right. Number 5. Oh, sorry. What do you conclude about the effect of the low-fat diet? Meh, doesn't work. Even if it would have said significant, 6.9 and 7.1 are really close together. It's not really that much. Okay, 5. A geography test was given to a simple random sample of 250 high school students in a certain large school district. One question involved an outline map of Europe with the countries identified only by number. The students were asked to pick Great Britain and France. As it turned out, 65.6 could find France, compared to 70.4 for Great Britain. Is the difference statistically significant, or can this be determined from the information given? I hope you checked the back on this one. So you solved it, and what did you get? So p-value 12%, we accept the null. But there's a problem. Does your choice for France affect your choice for England? It can. If you put France where England is, you get 0%. If you put France where France is, then that eliminates one place for England to go. So a 2-sample z-test can only be done when the first choice is totally independent of the second choice, like rolling a dice twice. If I were pulling numbers out of a bag without replacement, can I do a 2-sample z-test? Is my first draw independent of my second draw if I don't put them back in? No. Right? The first draw affects the second draw. If I do put it back in, then they are independent. So you can't do a 2-sample z-test unless they're independent. 6. Some years the Gallup poll asked respondents how much confidence they have in various American institutions. You may assume the results are based on a simple random sample of 1,000 persons per year. The samples are independent from year to year. In 2005, only 41% responded they had a great deal or quite a lot of confidence in the Supreme Court, compared to 50 in 2000. Is the difference real? So 0.41 on one side and 0.5 on the other. So the null, the difference is equal to 0. The alternative, the difference is greater than 0. And again, you could say less than 0, and then you would have a negative z-score, and then you could shade norm from negative z to negative 5, but we're just going to make it positive every time. Okay, So what is the square root of 0.41 times 0.59 without doing it in a calculator? It's close to 0.5, but it'll be 0.49 or 0.499 or 0.4999, something like that. So I'm just going to say that is 0.49. What is the square root of 0.5 times 0.5? That is 0.5. Okay, and often the book just calls them both 0.5, but that makes me a little nervous, so I don't do it. All right, so what is the square root of 0.49 squared plus 0.5 squared? It's going to be bigger than the average, but smaller than the sum. What do you get? Did you get, is it 0.707? I'm doing the SE difference. Oh, wow. Sorry. Okay, so divided by the square root of 1,000. Boy, that was bad. You know, if only I knew how to edit videos. I could go in and take that out. Okay, so what do you get for the SEs? Okay, now let's do this. Am I going too fast? Do you guys understand what's going on? You don't? I'm going too quick? Okay, so these people said yes in 2000. These people said yes in 2005, or the other way around. Okay, so we take those scores and we create SDs. The SD is simply the square root of the percentage times the people who said no. So it's the square root of the yeses times the nos. And you do that with both of them, and you end up with 0.49 on the first one and 0.5 on the second one. Now we have to turn them into standard error for percentage, which means we divide by the square root of the number of draws. So 0.49 divided by the square root of 1,000 is 1.55, and the square, or sorry, 0.5 divided by the square root of 1,000 is 1.58. Those are SE percentages. And because they're percentages, you actually get 0.0158, and you have to move the decimal place 2 spots. That's where we get 1.58. Okay? So 1.55 squared plus 1.55 squared, and then we take the square root. That is called the SE for the difference, because we don't really know which one's right. We're just going to see, do they differ from each other? Now, the difference we expect is the one that's listed in our null hypothesis. And we said 0. And the actual difference is 9%. What is the SE difference? 2.21. Okay, so I am going to take this distance and divide it by 2.21. So 9 divided by 2.21 gives me a z-score of 4.066, which is really far out there. So now I shade norm to see how much area is there to the right. Well, how much area is there between 4 and 5? Very little, right? Our calculator stops giving us information after 5. So the area that is to the right of 4 is essentially 0. So my p-value is 0%. What that means is there is practically a 0% chance to do a study and to end up 4 standard errors away from the actual value. Now, we don't know if our numbers are right, so we rest on the fact that it is extremely unlikely for a study to mess itself up that badly. It can happen, but it happens almost 0% of the time. And because of that, we don't think that these numbers differ by chance. and we say we reject the null and accept the alternative hypothesis, and there is a highly significant difference between the value of 41% and the value of 50%.